Okay, on page 50 of Ashby, you'll see figure 4.2, and this shows different modes of loading and stress states for objects that are under some sort of mechanical load. And you can see here that if you apply force to an object, you can have maybe the force in sort of a uniaxial tension, or you could have it in a uniaxial compression, that's B here. And if you were to look at a tiny little piece of material, somehow magnify a little section of that material, that's what this little box is showing here, is that what it would look like is essentially, a uniaxial set of tensile forces on this little box, or compressive forces on the box. Now, if you're actually bending something like a beam, on the top you'd see tension, on the bottom you'd see compression. If you had a shaft where you were trying to torque the shaft, you'd see inside this that a little element would actually be under what's called a shear stress state. Or if you had a pressure vessel, you'd have in a small section of this material under a biaxial stress state. So you'd see a tension along one, or on two, like in a plane, a tension on sort of, I would say, the X and the Y section of this plane. Now this diagram on page 51 shows different ways that we consider the stress. So in a uniaxial tension state, the force is applied over this area, and the stress is equal to force over the area, and then the strain is equal to the change in length over the original length. And then down in this diagram in B and C shows you how we represent shear stress and pressure. But we're going to focus really on this top one here. Okay, on page 56 in diagram 4.5, you'll see this great drawing shows at the very center, when you talk about strain, strain is really a response to some stimuli, and on this outer ring it shows you that the stimuli can be of different nature. They can be from a thermal field, which through the expansion coefficient, which is a material property, causes strain. It could be a magnetic field, which is going to create strain through the magnetostrictive constant, or it could be an electric field, or it could be a stress field, and through the elastic moduli you will see a strain development. Or another way of saying that is that these material properties in this blue ring right here are the metrics that we use to relate the stimulus to the response of strain. So in terms of stress and strain basics, the strain is something that develops in response to the stress. And there are different types of strain. There's strain that can be considered temporary. So we got strain here, and we have temporary strain. And strain that's temporary usually results in actually a change in volume that is recovered when the stress is removed. So and this type of strain is in the category of elastic strain. Now another type of strain, which is not temporary but which is permanent, does not result in a change in volume, but it results in a change in shape. So you have the change of volume equals 0, and essentially what is happening in this type of permanent deformation is that you're getting what's called plastic strain, and plastic strain doesn't recover to the original shape. So when you remove the stress, so on plastic strains, really what you're doing is you're moving atoms to accommodate the change in shape that is being caused by the stress. So in plastic deformation, you're essentially moving. I'm going to say moving, but what I want to say really is that you're rearranging the atoms. And in elastic deformation, it's just a temporary movement of the atoms. In elastic deformation, this involves stretching bonds, whereas in plastic deformation, you're actually rearranging atoms or molecules depending on whether you're deforming metals or ceramics or polymers.